We're about to embark on a journey that will take us beyond the familiar boundaries of our solar system, into realms that stretch both above and below the cosmic neighborhood we call home. Tonight, we're going to explore what lies in the vast spaces beyond Pluto's orbit, beyond the reach of our sun's warming light. We'll venture into territories so immense and mysterious that they challenge everything we think we know about our place in the universe. But before we drift into these cosmic depths, feel free to comment your time and location below. There's something beautifully humbling about contemplating the edges of our solar system while scattered across our small blue planet. The visuals are here to guide you, but there's absolutely no problem if you find yourself drifting off partway through this journey. Feel free to close your eyes, breathe deeply, and let your imagination soar beyond the boundaries of the known. If you find comfort in these gentle explorations of the cosmos, I'd be grateful if you'd consider subscribing and liking this video. It helps the algorithm discover more curious souls like us, who carry an amazing passion for understanding our universe. Let's begin this extraordinary voyage to the edges of everything we know. When most of us think about our solar system, we picture the familiar dance of planets around our sun. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, all spinning in their eternal orbits like clockwork. But here's something that might surprise you. What we typically call our solar system, that collection of 8 planets and their moons, represents only the tiniest fraction of the actual territory that belongs to our sun. Imagine you're standing in the center of a vast city, looking at the buildings immediately around you. You might think that's the entire city, but in reality, the urban sprawl extends far beyond what your eyes can see. The suburbs stretch for miles, connected by highways and dotted with neighborhoods you've never visited. Our solar system is remarkably similar. The planets we know and love are like that inner city, while the true boundaries of our sun's influence extend into cosmic suburbs so distant that light from our star barely reaches them. To understand what lies above and below our solar system, we first need to grasp just how enormous the sun's domain really is. The most distant planet, Neptune, orbits at about 2.8 billion miles from the sun. That seems impossibly far, doesn't it? But Neptune isn't even close to marking the edge of our solar system. Beyond Neptune lies a realm so vast and sparsely populated that it makes the space between planets seem crowded by comparison. This is where our journey truly begins, in the mysterious regions that extend far beyond the last planet. Here, in the cold darkness beyond Neptune, we encounter our first major landmark in the cosmic wilderness. It's called the Kuiper Belt, and it's home to some of the most fascinating objects in our solar system. Picture a vast ring of icy debris, like a cosmic junkyard filled with the leftover building materials from when our solar system was young. The Kuiper Belt stretches from roughly Neptune's orbit out to about 55 times the distance between Earth and the Sun. To put that in perspective, if Earth's orbit were the size of a dinner plate, the Kuiper Belt would extend to the far wall of a large room. Within this frozen realm drift thousands of objects, some no bigger than mountains, others large enough to be considered dwarf planets. The most famous resident of the Kuiper Belt is probably Pluto, that beloved world that was reclassified from planet to dwarf planet in 2006. But Pluto has company out there. Objects like Eris, Makemake, and Haumea call the Kuiper Belt home, each one a unique world with its own story to tell. These are ancient objects, cosmic fossils, that have remained largely unchanged since the solar system's formation over 4.5 billion years ago. They're like time capsules, preserving the conditions and materials from the very beginning of our cosmic neighborhood. Some of these Kuiper Belt objects have moons of their own, creating miniature systems within the larger chaos of the belt. But even the Kuiper Belt, vast as it is, represents only the beginning of our solar system's true extent. As we continue our journey outward, the space between objects grows larger and larger. The gravitational influence of our sun weakens, but it doesn't disappear entirely. We're entering a region where the very concept of distance becomes almost meaningless to our human minds. Beyond the Kuiper Belt lies something even more mysterious and extensive. It's called the Oort Cloud, and it represents perhaps the most alien environment within our sun's domain. Named after the Dutch astronomer Jan Oort, who first proposed its existence, this spherical shell of icy objects surrounds our entire solar system like a vast cosmic bubble. The Oort Cloud begins where the Kuiper Belt ends, but its outer boundary extends to truly mind-boggling distances. We're talking about objects orbiting our sun at distances of up to 100,000 times farther than Earth. If you could somehow travel at the speed of light, it would take you nearly 2 years to reach the outer edge of the Oort Cloud. This is a realm so distant that the sun appears as nothing more than a bright star among countless others. Within this cosmic sphere drift trillions of icy bodies, each one a potential comet, waiting for some gravitational disturbance to send it careening toward the inner solar system. These objects are the source of the long-period comets that occasionally grace our skies, visitors from the edge of everything carrying ice and dust from the solar system's earliest days. The Oort Cloud is divided into 2 distinct regions. The inner Oort Cloud, which is more disc-shaped and aligned with the plane of the planets, and the outer Oort Cloud, which forms a complete spherical shell around the entire solar system. Together, these regions contain more mass than all the planets combined, yet they're spread across such enormous volumes that the space between objects is virtually empty. Living in the Oort Cloud would be like floating in the deepest ocean of space. The sun would provide no warmth, appearing as just another point of light in the cosmic dark. Temperatures here hover just a few degrees above absolute zero, so cold that even helium would freeze solid. Time moves differently in this realm. Objects in the outer Oort Cloud take millions of years to complete a single orbit around the sun. Some may have orbited only a few dozen times since the solar system formed. But here's where our journey takes a fascinating turn. The Oort Cloud doesn't mark the true boundary of our solar system's influence. It marks something else entirely, something that connects us to the broader galaxy in ways that are both beautiful and profound. You see, the objects in the outer Oort Cloud are so loosely bound to our sun that they exist in a delicate gravitational balance. They're influenced not just by our sun, but by other stars, by molecular clouds drifting through the galaxy, and by the overall gravitational field of the Milky Way itself. These distant objects live at the intersection between our local solar system and the galaxy at large. This brings us to one of the most remarkable discoveries in modern astronomy. Our solar system doesn't exist in isolation, floating through empty space like a cosmic island. Instead, we're part of a much larger structure, embedded within streams of stars and clouds of gas and dust that flow through our local region of the galaxy. As our sun orbits the center of the Milky Way, carrying the entire solar system along with it, we pass through different galactic neighborhoods. Sometimes we're in regions of space that are relatively empty, and sometimes we encounter denser clouds of interstellar material. These passages through different galactic environments have profound effects on the outer reaches of our solar system. When our solar system encounters a dense molecular cloud or passes close to another star, the gravitational disturbances can shake up the Oort Cloud, sending showers of comets toward the inner planets. Some scientists believe that these galactic encounters may have contributed to mass extinction events in Earth's history, as increased comet activity brought both water and destruction to our planet. But the influence flows both ways. Just as the galaxy shapes the outer boundaries of our solar system also leaves its mark on the interstellar medium. As we move through space, the solar wind, that stream of charged particles flowing from our sun, carves out a protective bubble in the interstellar medium called the heliosphere. The heliosphere is like a cosmic force field, deflecting some of the high-energy cosmic rays that would otherwise bombard the inner planets. The boundary where the solar wind meets the interstellar medium is called the heliopause, and it represents the true edge of our sun's sphere of influence. Beyond this boundary, we enter interstellar space proper, where other stars hold sway. The Voyager spacecraft, launched in the 1970s, have given us our first direct measurements of this boundary. Voyager 1 crossed the heliopause in 2012, officially becoming the first human-made object to enter interstellar space. The data it sent back revealed that the transition from solar to interstellar space is not sharp but gradual, a complex boundary region where the influences of our sun and the galaxy blend together. As we continue our exploration of what lies above and below our solar system, we begin to see that these concepts of above and below are more complex than they might initially appear. In the three-dimensional reality of space, there is no universal up or down. The plane of our solar system, defined by the orbits of the major planets, provides a reference frame, but it's just one way of organizing our understanding of cosmic geography. Above and below the plane of the ecliptic, the solar system takes on different characteristics. The spherical nature of the Oort Cloud means that cometary objects exist in all directions around the Sun, creating a three-dimensional cloud of potential visitors. Some of these objects follow orbits that are highly inclined to the plane of the planets, swooping up and over and under the familiar realm of the 8 worlds we know best. This three-dimensional structure of our solar system connects us to the broader three-dimensional structure of the galaxy itself. The Milky Way is not a flat disk, but a complex spiral galaxy with a thick disk, a thin disk, a central bulge, and an extended halo of stars and dark matter. Our solar system sits within the thin disk, but our motion through the galaxy carries us above and below the galactic plane in a gentle oscillation that takes millions of years to complete. This galactic perspective reveals something profound about our cosmic address. We're not just residents of the solar system, or even just citizens of the Milky Way galaxy. We're part of an interconnected cosmic web that extends across the observable universe, where the boundaries between one system and another are fluid and constantly changing. This cosmic web extends far beyond what our eyes can see, even beyond what our most powerful telescopes can detect. Above and below our solar system, in directions that stretch perpendicular to the familiar plane of planetary orbits, lies a universe of connections that would humble even the most ambitious imagination. When we think about what exists above our solar system, we're really asking about the structure of space itself in directions that take us away from the ecliptic plane. If you could somehow stand on the North Pole of the Sun and look outward, you'd be gazing toward what astronomers call the North Galactic Pole. In this direction, roughly 27,000 light-years away, lies the center of our galaxy, hidden behind clouds of dust and gas that make direct observation impossible in visible light. But it's not just the galactic center that defines what lies above us. The space between our solar system and distant galactic structures is filled with something far more subtle and pervasive than most people realize. This is the realm of the galactic magnetic field. invisible threads of electromagnetic force that weave through space like cosmic highways, guiding the movement of charged particles across vast distances. These magnetic field lines don't respect the boundaries we imagine around our solar system. They flow through the heliopause as if it barely exists, connecting our local environment to regions of space so distant that light from them takes thousands of years to reach us. Along these magnetic highways, cosmic rays travel at nearly the speed of light, carrying information about stellar explosions and galactic processes that occurred long before human civilization began. Above our solar system, in the direction of the constellation Draco, lies one of the most significant features in our local galactic neighborhood. It's called the local bubble, a cavity in the interstellar medium roughly 300 light-years across. This bubble was carved out by the stellar winds and supernova explosions of massive stars that lived and died millions of years ago, creating a region of space where the density of gas and dust is unusually low. Our entire solar system sits near the edge of this local bubble, and our motion through the galaxy is currently carrying us deeper into it. This has profound implications for the environment our solar system experiences. The reduced density of interstellar material in the local bubble means less resistance to the solar wind, allowing our heliosphere to expand farther than it would in denser regions of space. But the local bubble is just one feature in a complex network of similar structures that astronomers call the local bubble complex. These interconnected cavities and tunnels in the interstellar medium create a kind of cosmic subway system, allowing hot gas and energetic particles to flow between different regions of our galactic neighborhood with surprising ease. Moving our perspective to look below our solar system, toward the South Galactic Pole, we encounter a different but equally fascinating set of cosmic structures. In this direction lies the Oort Belt, a ring of young, hot stars and star-forming regions that surrounds our solar system at distances ranging from a few hundred to a few thousand light-years. The Oort Belt is tilted at an angle to the main galactic plane, creating a local stellar environment that's quite different from what we'd expect if we were embedded in the average galactic disk. This belt includes some of the most recognizable stellar landmarks in our sky, including the bright stars of Orion, the Pleiades cluster, and the star-forming regions of Taurus and Perseus. What makes the Oort Belt particularly intriguing is that it appears to be expanding, as if all these stars and star-forming regions were set in motion by some ancient cosmic event. Some astronomers believe that a massive star, or even a series of supernovae explosions millions of years ago, created a shockwave that triggered star formation throughout this region, creating the structure we see today. This expanding ring of stellar activity has direct implications for our solar system's history and future. As we orbit the galaxy, our path occasionally takes us through or near active star-forming regions within the Oort Belt. During these passages, our solar system would be exposed to increased levels of cosmic radiation, potentially affecting our planet's climate and the evolution of life. Below our solar system, the view extends towards some of the nearest star systems that share our galactic neighborhood. The Alpha Centauri system, our closest stellar neighbors, lies roughly in this direction, along with dozens of other nearby stars that make up what astronomers call the local stellar neighborhood. These nearby stars aren't just distant lights in the sky. They're dynamic systems with their own planets, stellar winds, and magnetic fields that interact with our own solar environment in subtle but measurable ways. The gravitational influence of these nearby stars, while incredibly weak, accumulates over the billions of years of our solar system's existence, gently perturbing the orbits of objects in the outer Oort Cloud. Some of these stellar neighbors have already had close encounters with our solar system in the distant past, and others will do so in the future. About 70,000 years ago, a red dwarf star called Scholz's star passed through the outer regions of the Oort Cloud, coming within about a light year of our Sun. This encounter would have gravitationally disturbed countless cometary objects, potentially sending some of them on trajectories toward the inner solar system. Looking deeper into space, both above and below our solar system's plane, we begin to encounter the true scale of galactic structure. The Milky Way galaxy contains between 200 and 400 billion stars, organized into spiral arms that rotate around the galactic center like a cosmic pinwheel. Our solar system sits about halfway out from the center, in a relatively quiet region between the major spiral arms. This location has been crucial for the development of life on Earth. The spaces between spiral arms are regions of relative stability, where the density of stars is lower and the frequency of disruptive events like nearby supernovae or stellar collisions is reduced. If our solar system were located in one of the major spiral arms, the increased stellar density and activity might have made the evolution of complex life far more difficult or even impossible. Above and below our position in the galactic disk, the density of stars decreases rapidly. The thin disk of the galaxy, where most stars reside, has a thickness of only about 2,000 light-years, while the galaxy's diameter spans over 100,000 light-years. This means that if we could somehow travel perpendicular to the galactic plane, we would quickly find ourselves in the realm of the galactic halo. The galactic halo is one of the most mysterious components of our galaxy. It contains only about 1% of the Milky Way's stars, but these are some of the oldest stars in the galaxy, ancient suns that formed when the universe was young and had a very different chemical composition than it does today. These halo stars follow highly elliptical orbits that can take them far above and below the galactic plane, creating a sparse but extensive stellar population that surrounds the entire galaxy. Mixed in with these ancient stars are the globular clusters, dense balls of hundreds of thousands of stars that orbit the galactic center like cosmic satellites. These clusters are visible from Earth as fuzzy patches of light, but they represent some of the most extreme stellar environments in the galaxy. Within a globular cluster, stars are packed so densely that the night sky would be filled with brilliant suns, and planetary systems would be constantly disrupted by gravitational interactions. But perhaps the most significant component of the galactic halo is something we cannot see directly. The halo is dominated by dark matter, that mysterious substance that makes up about 85% of all matter in the universe, but interacts only through gravity. The dark matter halo extends far beyond the visible edges of our galaxy, creating a gravitational framework that holds the entire Milky Way together. This dark matter halo is not uniform, but contains substructures, streams and clumps that are the remnants of smaller galaxies that were torn apart and absorbed by the Milky Way over billions of years. These ghostly streams of dark matter and ancient stars flow through the space above and below our solar system, invisible evidence of our galaxy's violent and dynamic history. As our perspective expands even further, we begin to see that our galaxy itself is not alone in this region of the universe. The Milky Way is the largest member of a small group of galaxies called the Local Group, which contains about 80 galaxies in total, most of them small dwarf galaxies that orbit either our galaxy or the Andromeda Galaxy. The Local Group spans about 10 million light-years across, and our position within it gives us unique views in different directions. Above our solar system, looking toward the North Galactic Pole, we can see several of these neighboring galaxies, including the large spiral galaxy in Andromeda that is slowly approaching us and will eventually collide with the Milky Way in about 4.5 billion years. Below our solar system, toward the South Galactic Pole, lie the large and small Magellanic Clouds, irregular galaxies that are gravitationally bound to the Milky Way. These galaxies are currently being torn apart by tidal forces from our galaxy, creating streams of gas and stars that are slowly being incorporated into the Milky Way structure. This galactic cannibalism is not unusual in the universe. Galaxies grow by consuming smaller neighbors, and the Milky Way bears the scars of many such encounters in its past. The streams of stars and dark matter that flow above and below our solar system are evidence of these ancient cosmic collisions, frozen in time like fossil rivers in the gravitational landscape of our galaxy. The space between galaxies in the local group is not empty, but filled with a tenuous medium of hot gas, cosmic rays, and magnetic fields. This intergalactic medium connects all the galaxies in our local neighborhood, allowing them to exchange material and energy across millions of light years. Our solar system, while tiny on these scales, is part of this vast network of cosmic exchange. Beyond even these galactic scales, we encounter structures so vast, they challenge our understanding of space and time itself. Above and below our solar system, extending in directions that dwarf even the local group, lies the cosmic web, a network of dark matter filaments that connects galaxy clusters across hundreds of millions of light years. Picture the universe as a vast three-dimensional spider web, with galaxies strung like dewdrops along invisible threads of dark matter. Our local group sits on one of these cosmic filaments, part of a structure called the local supercluster, or Laniakea. This supercluster contains over 100,000 galaxies and spans more than 500 million light years across, yet it represents just a tiny fraction of the observable universe. The cosmic web creates a natural highway system through space, guiding the flow of matter and energy across cosmic distances. Along these dark matter filaments, galaxies migrate over billions of years, drawn by gravitational currents that operate on scales so large they're almost beyond comprehension. Our own galaxy is currently flowing along one of these cosmic streams toward a region of space called the Great Attractor, a gravitational anomaly that's pulling thousands of galaxies toward it at speeds of hundreds of kilometers per second. Between the filaments of the cosmic web lie vast voids, regions of space so empty they contain almost no galaxies at all. These cosmic voids can span hundreds of millions of light years across, creating caverns in the universe where matter is so sparse that traveling through them would be like floating through an ocean of darkness, punctuated only by the occasional island of light. Above our solar system, in certain directions, we look directly into some of these cosmic voids. The Buta's void, sometimes called the Great Nothing, is one such region roughly 330 million light years across. If our solar system were located in the center of this void, we would see almost no other galaxies in any direction, creating a night sky that would appear nearly empty to any observers on Earth. These voids are not truly empty, however. They contain dark matter, dark energy, and the occasional lonely galaxy that somehow avoided being pulled into the surrounding filaments. They also contain something even more mysterious: quantum fluctuations in the vacuum of space itself, tiny variations in energy that may hold clues to the fundamental nature of reality. The quantum vacuum that fills these cosmic voids is alive with activity at the smallest scales. Virtual particles pop in and out of existence in fractions of a second, creating a subtle energy that may be responsible for the accelerating expansion of the universe. This dark energy makes up about 68% of the universe's total energy content, yet we understand almost nothing about its nature or origin. As we contemplate what lies above and below our solar system on these cosmic scales, we begin to realize that our sun's gravitational influence extends into a universe that's far stranger and more dynamic than our ancestors could have imagined. The very space between galaxies is expanding, carrying distant structures away from us at ever-increasing speeds. This expansion means that there are regions of the universe that are receding from us faster than the speed of light, not because they're moving through space at such speeds, but because space itself is stretching between us and them. These regions lie beyond what astronomers call the cosmic horizon, the boundary beyond which we can never see, no matter how long we wait or how powerful our telescopes become. Above and below our solar system, in directions that point toward these most distant reaches of space, lie galaxies whose light will never reach us. They exist in a part of the universe that is causally disconnected from our own, creating islands of reality that will forever remain beyond our direct observation. Yet even these unreachable regions are connected to us through the fundamental forces and fields that permeate all of space. The electromagnetic field that surrounds our solar system is part of a universal field that extends to the very edge of the observable universe and beyond. The gravitational waves that ripple through space-time from colliding black holes and neutron stars carry information across cosmic distances, connecting us to events that occurred billions of years ago in regions of space we'll never directly see. These gravitational waves wash over our solar system constantly, creating tiny distortions in space and time that we've only recently learned to detect. They carry with them the signatures of cosmic catastrophes, stellar collisions, and the birth and death of massive objects throughout the universe. In a very real sense, our solar system exists within an ocean of gravitational waves that connect us to the most violent and energetic events in cosmic history. The magnetic fields that thread through space above and below our solar system are equally far-reaching. Generated by the rotation of planets, the nuclear fusion in stellar cores, and the accretion of matter around black holes, these magnetic fields create invisible networks that guide the flow of charged particles across galactic and intergalactic distances. Some of these magnetic field lines may connect our solar system to regions of space so distant that their light has been traveling toward us since shortly after the Big Bang. Along these cosmic magnetic highways, high-energy particles surf the electromagnetic waves, carrying information about conditions in the early universe and the processes that shape the cosmic structures we see today. As our journey through the realms above and below our solar system continues, we encounter one of the most profound mysteries in modern cosmology: the cosmic microwave background radiation. The afterglow of the Big Bang itself bathes our entire solar system in ancient light that has been traveling through space for nearly 14 billion years. This radiation comes to us from all directions, above and below, creating a kind of cosmic fossil record that preserves information about the universe when it was only 380,000 years old. The tiny variations in this background radiation, differences in temperature of only a few millionths of a degree, represent the seeds from which all cosmic structure eventually grew. Above our solar system, in the direction of certain constellations, we can observe regions of the cosmic microwave background that were slightly denser in the early universe. These overdense regions eventually collapsed under their own gravity to form the first stars and galaxies. Below our solar system, in other directions, we see regions that were slightly less dense, which became the voids and empty spaces between galaxy clusters. This ancient light carries with it information about the fundamental parameters of the universe, its age, its composition, and the rate at which it's expanding. By studying the cosmic microwave background from our position within the solar system, we're able to piece together the history of the entire observable universe, from its fiery birth to its current state of accelerating expansion. But perhaps the most remarkable aspect of what lies above and below our solar system is how it connects to the quantum world at the smallest scales. The vacuum of space that surrounds our solar system is not empty, but filled with quantum fields that extend throughout the universe. These fields fluctuate constantly at the quantum level, creating virtual particles that appear and disappear in fractions of a second. Some theoretical physicists believe that these quantum fluctuations in the vacuum may be responsible for the dark energy that's driving the accelerating expansion of the universe. If this is true, then the space above and below our solar system is literally humming with quantum activity that influences the fate of the entire cosmos. The boundary between our solar system and the larger universe is not sharp but gradual, a transition zone where the influence of our sun slowly gives way to the gravitational and magnetic fields of the galaxy. In this transition zone, the solar wind meets the interstellar medium, creating a complex boundary layer where particles from our sun mix with material that has traveled between the stars for millions of years. This boundary, known as the heliopause, is constantly shifting and changing as our solar system moves through different regions of the galaxy. Sometimes we encounter dense molecular clouds that compress our heliosphere, bringing the interstellar medium closer to the outer planets. Other times we pass through regions of lower density, allowing our sun's influence to extend farther into space. The dance between our solar system and the galaxy creates a constantly changing environment that has profound effects on the conditions within our cosmic neighborhood. During passages through dense interstellar clouds, the increased cosmic ray flux can affect planetary atmospheres and potentially influence climate patterns on Earth and other worlds. These galactic seasons operate on timescales of millions of years, far longer than human civilization, but they represent an important aspect of what lies beyond our solar system's boundaries. We are not isolated in space, but embedded in a dynamic galactic environment that shapes our local conditions in ways we're only beginning to understand. As we look above and below our solar system into these vast cosmic structures, we begin to see patterns that repeat at every scale. The same gravitational and electromagnetic forces that shape planetary orbits also guide the formation of galaxy clusters and superclusters. The same quantum fields that govern atomic interactions also permeate the space between stars and galaxies. This cosmic unity suggests that our solar system, small as it may be on cosmic scales, participates in physical processes that operate throughout the observable universe. The atoms in our bodies were forged in stellar cores that existed billions of years before our solar system formed, and the energy that powers our sun comes from nuclear processes that are occurring in stars throughout the galaxy and beyond. Above and below our solar system lies not just empty space or distant objects, but a vast network of physical processes and structures that connect us to the deepest mysteries of existence. We are part of a universe that is far more interconnected and dynamic than our everyday experience suggests, embedded in cosmic flows that carry us through space and time as passengers on a journey that began with the Big Bang and continues to unfold around us every moment. In contemplating these vast scales and connections, we gain a perspective that is both humbling and inspiring. Our solar system may be tiny compared to the structures that surround it, but it is also a unique and precious oasis of complexity and life in a universe that is still revealing its secrets to those patient enough to listen and observe. The space above and below our solar system is not empty void, but a rich tapestry of matter, energy, and information that connects us to the grandest scales of cosmic architecture. Every photon of starlight that reaches us has traveled through this cosmic web, carrying messages from distant realms that expand our understanding of what it means to exist in this vast and wondrous universe. The journey through these cosmic realms reveals something profound about the nature of space itself. As we venture further from our solar system's familiar boundaries, we discover that what appears to be empty void is actually teeming with invisible activity. The vacuum of space, rather than being truly empty, pulses with quantum fluctuations that occur at scales so small and times so brief that they exist at the very edge of physical possibility. These quantum fluctuations create virtual particles that pop into existence and vanish again in microseconds, borrowing energy from the universe itself before paying it back. This constant dance of creation and annihilation fills every cubic centimeter of space above and below our solar system, creating what physicists call zero-point energy. This energy may seem insignificant, but when multiplied across the vast volumes of interstellar and intergalactic space, it becomes one of the driving forces behind cosmic expansion. As we drift deeper into contemplation of these scales, we begin to understand that our solar system exists within multiple nested spheres of influence. Beyond the obvious gravitational pull of our Sun lies the more subtle influence of tidal forces from the galactic center. These tidal forces are incredibly weak, but over the billions of years since our solar system formed, they have gently sculpted the orbits of the most distant objects in the Oort Cloud. The galactic tides work like cosmic hands, slowly stretching and compressing the outer regions of our solar system as we orbit the Milky Way's center. This process has scattered some cometary objects into interstellar space, while capturing others that originally belonged to different stellar systems. In this way, our solar system has been slowly exchanging material with the galaxy for its entire existence. Above our solar system, in directions that take us toward the galactic poles, we encounter streams of stars that tell stories of ancient cosmic violence. These stellar streams are the stretched out remains of smaller galaxies and star clusters that were torn apart by the Milky Way's gravitational field over billions of years. Like cosmic rivers frozen in space, these streams flow through the galactic halo, carrying with them the chemical signatures of stellar populations that formed under very different conditions than our Sun. Some of these stellar streams pass relatively close to our solar system, astronomically speaking. The Sagittarius stream, for example, wraps around our galaxy multiple times, creating loops and arcs of ancient stars that are slowly being absorbed into the Milky Way's structure. When our solar system's orbit carries us near these streams, we're essentially passing through the remnants of galaxies that were destroyed billions of years ago. The gravitational influence of these passing stellar streams, while incredibly subtle, may have contributed to periodic disturbances in the Oort Cloud throughout our solar system's history. Some researchers have proposed that these galactic encounters could be responsible for some of the mass extinction events in Earth's past, as increased comet activity brought both life-giving water and devastating impacts to our planet. Below our solar system, extending toward the southern galactic pole, lies a region of space that contains some of the most energetic phenomena in our local cosmic neighborhood. Here we find the remnants of ancient supernovae, expanding shells of gas and magnetic fields that continue to accelerate particles to incredible energies millions of years after the original stellar explosions. These supernova remnants create cosmic particle accelerators that dwarf anything we can build on Earth. Within their twisted magnetic fields, protons and other atomic nuclei are accelerated to nearly the speed of light, becoming cosmic rays that then travel throughout the galaxy. Some of these cosmic rays, born in supernova explosions that occurred before our solar system even existed, are still traveling through space and occasionally strike Earth's atmosphere. The cosmic ray environment that bathes our solar system is constantly changing as we move through different regions of the galaxy. During our passages through the spiral arms, where massive stars are more common and supernova explosions more frequent, the cosmic ray flux increases significantly. These periods of increased radiation may have influenced the evolution of life on Earth and the other planets in ways we're only beginning to understand. The magnetic fields that permeate the space above and below our solar system create invisible highways for these cosmic rays, guiding their paths across vast distances. These galactic magnetic fields are generated by the rotation of the galaxy itself, creating a complex network of field lines that thread through interstellar space like cosmic DNA. Where these magnetic field lines intersect and reconnect, they release enormous amounts of energy in processes similar to solar flares, but on galactic scales. These magnetic reconnection events can accelerate particles to extreme energies and generate bursts of radiation that propagate across thousands of light years. Our solar system occasionally passes through regions where these energetic events are more common, exposing us to increased levels of high-energy radiation. The interstellar medium that fills the space between stars is far from uniform. Above and below our solar system lie bubbles and cavities carved out by stellar winds and supernova explosions, creating a foam-like structure in the gas and dust between stars. These bubbles can span hundreds of light years across, and their walls are often sites of active star formation, where compressed gas and dust collapse to form new stellar systems. Our solar system currently resides within one such bubble, known as the local bubble or local cavity. This region of hot, low-density gas was excavated by a series of supernova explosions that occurred roughly 10 to 20 million years ago. The reduced density of material in the local bubble allows our sun's solar wind to extend farther into space than it would in denser regions, creating a larger heliosphere that provides additional protection from cosmic radiation. But our stay in the local bubble is temporary. As our solar system orbits the galaxy, we're slowly moving toward the edge of this cavity and will eventually emerge into denser regions of the interstellar medium. When this happens, the increased pressure from surrounding gas and dust will compress our heliosphere, potentially allowing more cosmic radiation to penetrate into the inner solar system. The local bubble is connected to other similar structures through a network of channels and tunnels in the interstellar medium. These connections allow hot gas to flow between different regions, creating currents in the galactic medium that operate on scales of hundreds of light years. Our solar system rides these currents like a leaf on a cosmic stream. Our motion through the galaxy influenced by forces that operate far beyond our sun's gravitational reach. Above our solar system, in the direction of the constellation Ursa Major, lies one of the most significant structures in our local galactic environment. The Ursa Major moving group, also known as the Sirius supercluster, is a loose association of stars that share similar motions through the galaxy. These stars, scattered across a region roughly 30 light years across, were likely born together in the same star-forming region roughly 500 million years ago. What makes this stellar association particularly interesting is that our solar system appears to be on the edge of this moving group, suggesting that our sun may have formed in the same general region of the galaxy as these other stars. If this is true, then the stars of the Ursa Major moving group are distant siblings of our sun, born from the same giant molecular cloud that collapsed to form multiple stellar systems. The gravitational influence of this stellar association, while extremely weak, may have subtle effects on the long-term stability of orbits in the outer solar system. Computer simulations suggest that the combined gravitational pull of the moving group stars could influence the orbits of objects in the Oort Cloud over millions of years, potentially affecting the rate at which comets are sent toward the inner planets. Below our solar system, extending toward the constellation Puppis, lies another significant feature of our local galactic neighborhood. The Gum Nebula, a vast shell of ionized gas roughly 1,400 light-years across, represents one of the largest structures visible in our local region of the galaxy. This ancient supernova remnant continues to expand outward from explosions that occurred roughly 1 million years ago. The Gum Nebula is so large that it subtends a significant portion of the southern sky as seen from Earth. Yet it's so tenuous that its presence was only discovered in the mid-20th century. The hot, ionized gas within this nebula glows faintly in hydrogen light, creating a ghostly backdrop against which we see more distant stars and galaxies. Our solar system lies near the edge of the Gum Nebula, and some researchers have suggested that we may actually be inside its outer boundaries. If this is the case, then the interstellar medium in our immediate galactic neighborhood has been significantly altered by this ancient supernova explosion, with implications for the cosmic ray environment and magnetic field structure around our solar system. The expansion of the Gum Nebula and similar structures creates compression waves in the interstellar medium that can trigger the formation of new stars. These waves of stellar birth propagate through the galaxy like cosmic wildfires, creating chains of star formation that connect stellar nurseries across vast distances. Our own solar system may have been born in one such triggered star formation event, its birth catalyzed by shock waves from ancient stellar explosions. The space above and below our solar system also contains the remnants of our galaxy's violent past encounters with smaller galaxies. The Milky Way has been consuming its neighbors for billions of years, and the evidence of this galactic cannibalism is written in streams of stars that flow through the space around us. The Helmi Stream, the Sequoia Stream, and dozens of other stellar rivers represent the scattered remains of galaxies that were torn apart and digested by our own. These galactic merger events have not only added stars to the Milky Way, but have also stirred up the dark matter halo that surrounds our galaxy. Computer simulations show that the dark matter in our local region has been mixed and churned by these ancient collisions, creating a complex distribution of invisible matter that influences the motion of stars and gas throughout the galaxy. The dark matter that pervades the space above and below our solar system is not smoothly distributed, but clumpy and structured, containing subhalos and streams left over from the destruction of smaller dark matter concentrations. These dark matter substructures are completely invisible to our telescopes, but their gravitational effects can be detected through their influence on the motion of stars and the bending of light from more distant galaxies. Some of these dark matter clumps may pass very close to our solar system, or even through it, without our being able to detect them directly. Their passage would create subtle gravitational perturbations that might affect the orbits of objects in the outer solar system, but these effects would be so small that they would be virtually impossible to measure with current technology. The possibility that our solar system regularly encounters dark matter substructures adds another layer of complexity to our understanding of what lies beyond our cosmic neighborhood. We may be swimming in an ocean of invisible matter that is constantly flowing past us, carrying with it the gravitational echoes of cosmic events that occurred billions of years ago. Beyond these local dark matter structures lies the larger scaffolding of the cosmic web, the network of dark matter filaments that connects galaxy clusters across hundreds of millions of light years. Our local group of galaxies sits on one of these cosmic filaments, part of a vast river of matter that flows toward the Virgo cluster and beyond. This cosmic flow carries our entire galaxy group through space at speeds of hundreds of kilometers per second, part of a vast migration of matter toward regions of higher gravitational attraction. The Shapley supercluster, located roughly 650 million light-years away in the direction of the constellation Centaurus, exerts a gravitational pull that influences the motion of thousands of galaxy groups, including our own, above and below our solar system. In directions perpendicular to this cosmic flow, we can observe the structure of the cosmic web itself. Dark matter filaments stretch across the observable universe like a vast three-dimensional spiderweb, with galaxy clusters strung along them like pearls on cosmic strings. Between these filaments lie enormous voids, regions of space so empty that they contain almost no ordinary matter at all. These cosmic voids are not truly empty, however. They contain dark energy, the mysterious force that is driving the accelerating expansion of the universe. The nature of dark energy remains one of the greatest puzzles in modern physics, but its effects are observable on the largest scales of cosmic structure. It acts like a kind of anti-gravity, pushing space itself apart and causing distant galaxies to recede from us at ever-increasing speeds. The dark energy that fills the space above and below our solar system is responsible for the ultimate fate of the universe. If its properties remain constant, the universe will continue to expand forever, eventually leading to a state where all the stars have burned out and only black holes remain. Even these will eventually evaporate through Hawking radiation, leaving behind a universe filled with nothing but elementary particles separated by vast distances. But dark energy's properties may not remain constant. Some theoretical models suggest that it could change over time, potentially leading to even more dramatic scenarios for the universe's future. If dark energy continues to strengthen, it could eventually overcome not just gravity, but all the fundamental forces, leading to a Big Rip scenario, where even atoms are torn apart by the expanding space. Alternatively, dark energy could weaken or even reverse sign, causing the universal expansion to slow down and eventually reverse. This would lead to a Big Crunch scenario, where all matter and energy in the universe would eventually collapse back into a singular state, perhaps setting the stage for a new cosmic cycle. The quantum fields that permeate the space above and below our solar system may hold the key to understanding dark energy's true nature. According to quantum field theory, even empty space is filled with fluctuating energy fields that could, in principle, contribute to the cosmic expansion. However, when physicists calculate the expected magnitude of this quantum vacuum energy, they get a result that is larger than the observed dark energy density by a factor of 10 to the power of 120, one of the largest discrepancies between theory and observation in all of science. This enormous mismatch suggests that our understanding of the quantum vacuum is fundamentally incomplete. The space around our solar system may be filled with exotic forms of matter and energy that we have not yet learned to detect or understand. Virtual particles, quantum fluctuations, and vacuum energy may interact in ways that create the dark energy we observe, but the mechanism remains a mystery. The cosmic microwave background radiation that bathes the space above and below our solar system provides a window into the universe's earliest moments, when it was only 380,000 years old. This ancient light carries with it the imprint of quantum fluctuations that existed in the primordial universe, stretched to cosmic scales by the rapid expansion of space during the inflationary epoch. The tiny temperature variations in the cosmic microwave background, only a few parts per million, represent the seeds from which all cosmic structure eventually grew. Regions that were slightly denser than average eventually collapsed under their own gravity to form the first stars and galaxies, while regions that were slightly less dense became the voids and empty spaces between galaxy clusters. By studying the patterns in this ancient radiation, astronomers can determine fundamental properties of the universe, including its age, composition, and geometry. The results show that ordinary matter makes up only about 5% of the universe's total energy content, with dark matter contributing about 27% and dark energy making up the remaining 68%. This cosmic inventory reveals that the vast majority of the universe consists of substances that we cannot directly observe or fully understand. The space above and below our solar system is dominated by invisible components whose nature remains mysterious despite decades of intensive research. The cosmic microwave background also carries subtle signatures of gravitational waves that may have been produced during the universe's inflationary epoch. These primordial gravitational waves would provide direct evidence for the rapid expansion of space that occurred in the first fraction of a second after the Big Bang, offering insights into physics at energy scales far beyond anything achievable in terrestrial laboratories. Modern gravitational wave detectors have opened a new window on the universe, allowing us to observe the ripples in space-time created by colliding black holes and neutron stars. These cosmic collisions occur throughout the universe, creating gravitational waves that propagate at the speed of light and carry information about some of the most violent events in cosmic history. The gravitational waves that wash over our solar system provide a direct connection to events occurring in the most distant reaches of the observable universe. When two black holes collide in a galaxy, billions of light years away, the gravitational waves they produce eventually reach us, carrying with them information about the masses and spins of the colliding objects. These gravitational wave signals arrive at Earth after traveling through the cosmic web, passing through dark matter halos, interstellar gas clouds, and the gravitational fields of countless stars and galaxies. Yet they arrive virtually unchanged, providing an unobstructed view of cosmic events that would be impossible to observe through electromagnetic radiation alone. The detection of gravitational waves has confirmed one of Einstein's most profound predictions and opened up an entirely new field of astronomy. As our detectors become more sensitive, we will be able to observe gravitational waves from increasingly distant and exotic sources, potentially including the Big Bang itself. The space above and below our solar system resonates constantly with these gravitational waves, creating tiny distortions in the fabric of space-time that are now detectable by our most sophisticated instruments. Every passing gravitational wave stretches and compresses space by amounts smaller than 1,000th of a proton's width. Yet these minuscule effects carry information about cosmic events of unimaginable violence and energy. As we contemplate these vast scales and invisible influences, we begin to understand that our solar system exists within a universe that is far more dynamic and interconnected than our everyday experience suggests. The space around us hums with quantum activity, flows with dark matter streams, and pulses with gravitational waves from cosmic catastrophes occurring billions of light years away. Above and below our familiar planetary neighborhood lies not empty void, but a rich tapestry of physical processes operating on scales that range from the quantum to the cosmic. We are embedded in this web of interactions, influenced by forces that operate across distances so vast they challenge our ability to comprehend them, yet connected to the most fundamental processes that govern the behavior of matter, energy, space, and time throughout the observable universe. The gravitational waves that wash over our solar system connect us to phenomena so exotic they seem to belong to science fiction rather than observable reality. Deep in the space above our solar system, in directions that point toward distant galaxy clusters, massive black holes spiral toward each other in death dances that can last millions of years. These cosmic monsters, some containing the mass of billions of suns, warp space-time so severely that the very concepts of space and time begin to break down near their event horizons. When these supermassive black holes finally merge, they release more energy in gravitational waves than all the stars in the observable universe emit in light. The space-time ripples from these titanic collisions propagate outward at the speed of light, carrying with them information about conditions so extreme that matter behaves in ways we can barely comprehend. As these gravitational waves pass through our solar system, they interact with every atom in our bodies, every molecule in the air around us, stretching and compressing the very fabric of reality by amounts so small they exist at the boundary between the measurable and the theoretical. Yet within these infinitesimal distortions lies encoded information about the most energetic events in cosmic history. The space below our solar system, extending toward regions where ancient light has been traveling since the universe was young, contains gravitational wave echoes from events that occurred when the cosmos was a very different place. In those early epochs, when the universe was denser and hotter, black hole mergers were more frequent, and the gravitational wave background was correspondingly more intense. Some theoretical physicists propose that this primordial gravitational wave background might still be detectable today, a cosmic fossil record of the universe's violent youth preserved in the subtle vibrations of space-time itself. Detecting this ancient signal would provide unprecedented insights into the conditions that existed in the first moments after the Big Bang, when the fundamental forces of nature were unified and the laws of physics operated under conditions we can barely imagine. The magnetic fields that thread through the space surrounding our solar system create invisible sculptures in the interstellar medium, guiding the flow of charged particles across distances that dwarf our planetary system. These cosmic magnetic highways are not static, but constantly evolving, twisted and braided by the rotation of the galaxy and the turbulent motions of interstellar gas. Where magnetic field lines of opposite polarity come into contact, they can suddenly reconnect in explosive events that release enormous amounts of energy. These magnetic reconnection events, similar to solar flares but occurring on galactic scales, can accelerate particles to incredible speeds and generate bursts of radiation that propagate across thousands of light years. Our solar system occasionally passes through regions where the interstellar magnetic field is particularly strong or complex, exposing us to increased levels of cosmic radiation and potentially affecting the behavior of our sun's own magnetic field. These interactions between our local solar environment and the larger galactic magnetic field create a constantly changing cosmic weather system that operates on scales both vast and intimate. The cosmic rays that rain down upon our solar system from the space above and below carry with them the signatures of their violent births in the most extreme environments the universe can produce. Some originate in supernova explosions that occurred millions of years ago, while others are accelerated in the jets of material streaming from supermassive black holes at the centers of distant galaxies. These high-energy particles, traveling at nearly the speed of light, have journeyed across vast distances to reach us, deflected and scattered by magnetic fields, slowed by interactions with interstellar gas, yet still carrying information about their origins encoded in their energies and arrival directions. The most energetic cosmic rays possess energies so high that they challenge our understanding of how particles can be accelerated to such extremes. These ultra-high-energy cosmic rays, with energies equivalent to baseballs traveling at highway speeds, compressed into single atomic nuclei, arrive at Earth so rarely that detecting them requires vast arrays of instruments spread across thousands of square kilometers. The sources of these most energetic particles remain mysterious, hidden somewhere in the space above and below our solar system, in regions so distant that their light may have been traveling toward us since the universe was young. Active galactic nuclei, gamma-ray bursts, and exotic objects we have not yet discovered all remain candidates for the cosmic accelerators capable of producing such extreme energies. As these cosmic ray particles interact with Earth's atmosphere, they create cascades of secondary particles that rain down upon the surface like invisible snow. Every second, billions of these particles pass through our bodies, most without any detectable effect. Yet their presence connects us directly to the most violent processes occurring in distant corners of the universe. The interstellar dust that pervades the space around our solar system tells its own story of cosmic evolution and stellar death. These tiny grains, each smaller than the particles in cigarette smoke, are forged in the atmospheres of dying stars and scattered into space by stellar winds and supernova explosions. Above our solar system, in directions that point toward the galactic center, this dust becomes so dense that it blocks our view of the Milky Way's heart, creating dark lanes and patches in the star fields visible to our telescopes. This cosmic dust is not merely an obstacle to observation, but an active participant in the processes of stellar birth and death, serving as the raw material from which new stars and planetary systems eventually form. The dust grains act as tiny laboratories where complex chemistry occurs in the cold vacuum of space. On their surfaces, simple molecules combine to form more complex compounds, including some of the organic molecules that are essential for life as we know it. These dust grain factories operate continuously throughout the galaxy, slowly enriching the interstellar medium with the chemical building blocks of complexity. When our solar system encounters regions of higher dust density, the increased absorption and scattering of sunlight can affect the amount of energy reaching the outer planets. Over the billions of years of our solar system's existence, these variations in the interstellar environment may have contributed to long-term climate changes on Earth and influenced the evolution of life in ways we are only beginning to understand. The molecular clouds that drift through the space above and below our solar system represent some of the coldest and densest regions in the galaxy. These vast structures, some spanning hundreds of light years across, contain enough material to form thousands of stars like our Sun, yet they remain in a delicate balance between gravitational collapse and the pressure of their own internal motions. Within these molecular clouds, temperatures can drop to just a few degrees above absolute zero, creating conditions where exotic chemistry becomes possible. Complex organic molecules, including some that are precursors to the biochemistry of life, form in these frigid environments, suggesting that the ingredients for biology may be widespread throughout the galaxy. The passage of our solar system through or near these molecular clouds would have profound effects on our local environment. The increased density of surrounding material would compress our heliosphere, allowing more cosmic radiation to penetrate into the inner solar system. The gravitational influence of these massive clouds might also perturb the orbits of objects in the Oort Cloud, potentially triggering increased comet activity. Some researchers have proposed that encounters with molecular clouds might be responsible for some of the periodic mass extinction events in Earth's history, as the combination of increased cosmic radiation and comet impacts created challenging conditions for life on our planet. These cosmic catastrophes, operating on timescales of tens of millions of years, remind us that our solar system's journey through the galaxy exposes us to influences that operate far beyond our Sun's protective embrace. The stellar nurseries embedded within these molecular clouds represent the future of our galaxy, regions where new stars are being born from the gravitational collapse of dense cores within the larger structure. These star-forming regions glow with the light of young hot stars that have recently ignited nuclear fusion in their cores, illuminating the surrounding gas and dust in spectacular displays of cosmic beauty. Above our solar system, the Orion Nebula serves as the nearest major star-forming region, a cosmic laboratory where we can observe the processes of stellar birth occurring in real time. The intense radiation from the young stars within this nebula is slowly dispersing the surrounding molecular cloud, creating cavities and shells in the interstellar medium that will influence star formation in the region for millions of years to come. The shock waves generated by these stellar nurseries propagate through the surrounding medium, compressing nearby molecular clouds and potentially triggering new episodes of star formation in a process that can spread across vast regions of the galaxy. Our own solar system may have been born in such a triggered star formation event, its birth catalyzed by shockwaves from stellar nurseries that have long since dispersed. The heavy elements that make up the rocky planets in our solar system were synthesized in the nuclear furnaces of stars that lived and died before our sun was born. These stellar ancestors, scattered throughout the space above and below our current position, enriched the interstellar medium with carbon, oxygen, silicon, and iron through their stellar winds and explosive deaths. The supernova explosions that marked the end of these massive stars created expanding shells of hot gas that continue to influence the structure of the interstellar medium millions of years after the original explosions. These supernova remnants serve as cosmic particle accelerators, generating the high-energy cosmic rays that permeate our galactic neighborhood and influence the chemistry and physics of the space around our solar system. The neutron stars left behind by some supernova explosions represent some of the most extreme objects in the universe, with densities so high that a teaspoon of neutron star material would weigh as much as a mountain. These stellar remnants, spinning rapidly and generating intense magnetic fields, emit beams of radiation that sweep across space like cosmic lighthouses. When these beams happen to point in our direction, we detect them as pulsars, cosmic clocks that keep time with incredible precision. The timing of pulsar signals has allowed astronomers to detect gravitational waves, test theories of gravity, and even search for planets orbiting these exotic stellar remnants. The space above and below our solar system contains hundreds of these neutron stars, most too faint or poorly aligned to be detected as pulsars. Yet each one represents the compressed core of a star that once shone brightly in our galactic neighborhood. Their gravitational fields, while weak at our distance, contribute to the overall gravitational environment that guides our solar system's motion through the galaxy. Some neutron stars exist in binary systems with other stars, slowly accreting material from their companions in processes that can lead to spectacular thermonuclear explosions on their surfaces. These X-ray bursts release as much energy in seconds as our sun emits in months, creating brilliant flashes of high-energy radiation that can be detected across galactic distances. The white dwarf stars that represent the final fate of stars like our sun are scattered throughout the space surrounding our solar system, cooling slowly from their formation temperatures of hundreds of thousands of degrees. These stellar remnants, no larger than Earth but containing the mass of the sun, will continue to cool for trillions of years, eventually becoming cold, dark objects that persist long after all other stars have burned out. Some white dwarfs exist in binary systems where they accrete material from companion stars, building up layers of hydrogen and helium on their surfaces until conditions become right for explosive nuclear fusion. These thermonuclear explosions, known as type Ia supernovae, are among the most energetic events in the universe and serve as standard candles for measuring cosmic distances. The space around our solar system bears the chemical signatures of these stellar explosions, enriched with iron peak elements forged in the extreme conditions of thermonuclear detonation. The iron in our blood, the nickel in Earth's core, and many other heavy elements essential for rocky planet formation were created in these stellar furnaces and scattered into space by the explosive winds of dying stars. The brown dwarfs that populate the space above and below our solar system represent failed stars, objects massive enough to begin nuclear fusion but too small to sustain the process for billions of years. These substellar objects, glowing dimly in infrared light from their residual heat, may be among the most common objects in the galaxy, yet their faintness makes them difficult to detect and study. Recent surveys have revealed that brown dwarfs come in a surprising variety of types, with different atmospheric compositions and temperatures that create complex weather patterns in their thick atmospheres. Some brown dwarfs show evidence of auroras powered by magnetic field interactions, while others exhibit dramatic changes in brightness due to rotating storm systems. The nearest brown dwarfs to our solar system may lie closer than some of the faintest red dwarf stars, hidden in the darkness between the stars and detectable only through their gravitational effects or faint infrared glow. These stellar nomads represent a significant component of the galaxy's mass budget, contributing to the overall gravitational environment that shapes the structure of the Milky Way. The rogue planets that drift through the space around our solar system tell stories of cosmic violence and gravitational disruption. These world-sized objects, ejected from their birth systems by close encounters with other planets or stellar companions, wander through interstellar space as lonely orphans, warmed only by the decay of radioactive elements in their cores. Computer simulations suggest that there may be more rogue planets in the galaxy than there are stars, creating a vast population of wandering worlds that exist in the cold darkness between stellar systems. Some of these rogue planets may retain thick atmospheres that provide insulation, potentially maintaining liquid water oceans beneath their frozen surfaces. The possibility that some rogue planets might harbour life, sustained by geothermal energy rather than stellar radiation, expands our understanding of where life might exist in the universe. These dark worlds, drifting through the space above and below our solar system, represent an entirely different category of potentially habitable environments that we are only beginning to consider. Occasionally, a rogue planet might pass close enough to our solar system to be detected through its gravitational effects on known objects, or through direct observation with infrared telescopes. Such encounters would provide unique opportunities to study these mysterious wanderers and learn about the violent processes that ejected them from their original homes. The space above and below our solar system pulses with neutrinos, ghostly particles produced in nuclear reactions throughout the universe. These nearly massless particles interact so weakly with matter that they can pass through entire planets without being absorbed, creating an invisible flood of information about nuclear processes occurring in stellar cores, supernova explosions, and other high-energy phenomena. Billions of neutrinos pass through every square centimeter of space every second, most of them produced in the nuclear fusion reactions occurring in the Sun's core. But mixed in with this solar neutrino flux are messengers from far more exotic sources: collapsing stellar cores, accretion disks around black holes, and cosmic ray interactions in distant galaxies. The detection of high-energy neutrinos from extragalactic sources has opened a new window on the universe, allowing astronomers to study cosmic accelerators and nuclear processes that would be impossible to observe through electromagnetic radiation alone. These neutrino telescopes, built in deep ice or underwater to shield them from other particles, represent humanity's most sensitive detectors for studying the high-energy universe. The neutrinos streaming through the space around our solar system carry with them information about conditions in the cores of stars, the moments of stellar collapse that create neutron stars and black holes, and the acceleration mechanisms operating in the jets of active galactic nuclei. Each detected neutrino represents a direct sampling of nuclear processes occurring under conditions of extreme temperature, density, and magnetic field strength. As neutrino astronomy continues to develop, we may soon be able to observe neutrino sources that are completely invisible to conventional telescopes, hidden behind dust clouds or obscured by the bright emission from surrounding material. These hidden cosmic accelerators, scattered throughout the space above and below our solar system, may represent some of the most energetic and violent processes occurring in our local galactic neighborhood. The dark matter streams that flow through the space surrounding our solar system create invisible currents in the cosmic ocean, carrying with them the gravitational echoes of ancient galaxy mergers and the slow evolution of cosmic structure over billions of years. These streams, detectable only through their gravitational effects, represent the remnants of smaller dark matter halos that have been torn apart and stretched by the Milky Way's tidal forces. Computer simulations of galaxy formation predict that our local region should be crisscrossed by dozens of these dark matter streams, each one following its own orbit through the galactic halo. The density and velocity structure of these streams encode information about the merger history of our galaxy and the properties of dark matter particles themselves. Some of these dark matter streams may be dense enough to create detectable effects in dark matter detection experiments, creating seasonal variations in detection rates as Earth's orbit carries us through different parts of the streams. The search for these subtle signals represents one of the most promising approaches to directly detecting dark matter particles and confirming their existence through laboratory measurements. The gravitational effects of dark matter streams may also influence the orbits of objects in the outer solar system over very long timescales, creating subtle perturbations that could potentially be detected through precise measurements of orbital elements. These effects would be incredibly small, but they might provide indirect evidence for the dark matter structures flowing through our local galactic neighborhood. The space above and below our solar system resonates with gravitational waves from sources so distant that their light has been traveling toward us since the universe was a fraction of its current age. These ancient signals carry information about cosmic events that occurred when the universe was denser, hotter, and filled with objects and processes that no longer exist in the modern cosmos. Primordial black holes, if they exist, would be remnants of the universe's earliest moments, formed not from stellar collapse, but from the direct gravitational collapse of dense regions in the primordial plasma. These exotic objects, ranging in mass from asteroids to stars, would emit gravitational waves as they merge with each other, or with conventional black holes formed from stellar collapse. The detection of gravitational waves from primordial black hole mergers would provide direct evidence for physics operating under the extreme conditions that existed in the universe's first moments. These signals would carry with them information about the density fluctuations that existed in the primordial cosmos and the processes that determined how matter clumped together to form the first structures. Cosmic strings, if they exist, would be one-dimensional defects in the fabric of space-time itself, stretching across cosmic distances and vibrating with oscillations that generate gravitational waves. These theoretical objects, predicted by some models of cosmic inflation, would create distinctive gravitational wave signatures that could be distinguished from the signals produced by black hole and neutron star mergers. The space around our solar system may be threaded by these cosmic strings, invisible to electromagnetic observations, but potentially detectable through their gravitational wave emissions. The discovery of cosmic strings would revolutionize our understanding of the universe's earliest moments and provide insights into the fundamental physics operating at energy scales far beyond anything achievable in terrestrial laboratories. As we drift deeper into contemplation of these cosmic mysteries, we begin to see that the space above and below our solar system contains not just matter and energy, but information itself. Every particle that passes through our region of space, every gravitational wave that ripples through space-time, every neutrino that streams past our planet carries encoded within it the history of cosmic processes operating across vast scales of space and time. This information, scattered throughout the invisible medium that surrounds our solar system, represents a kind of cosmic library containing the accumulated knowledge of billions of years of cosmic evolution. The challenge for humanity is learning to read this library, to decode the messages written in the language of particle physics, gravitational waves, and electromagnetic radiation. The techniques we are developing to detect and interpret these cosmic signals represent some of the most sophisticated technologies ever created, pushing the boundaries of what is possible in terms of sensitivity, precision, and data analysis. These instruments, scattered across Earth and orbiting in space, transform our planet into a cosmic observatory capable of detecting signals from the most distant reaches of the observable universe. Every detection, every measurement, every data point adds to our understanding of what lies beyond our solar system's boundaries. We are slowly piecing together a picture of our cosmic neighborhood that is far richer, more dynamic, and more interconnected than previous generations could have imagined. The space above and below our solar system reveals itself to be not empty void, but a vast network of physical processes and structures that connect us to the deepest mysteries of existence. We are embedded in this cosmic web, participants in processes that operate on scales from the quantum to the cosmological, temporary arrangements of matter and energy that have achieved the remarkable ability to contemplate our own cosmic context. In understanding what lies beyond our familiar planetary neighborhood, we gain perspective on our place in the grand story of cosmic evolution, a story that began with the Big Bang and continues to unfold around us in ways both subtle and profound. The journey through these realms of space and time reminds us that we are not isolated observers of the universe, but active participants in its ongoing dance of matter, energy, and information across the vast scales of cosmic architecture. As we float through these contemplations of cosmic vastness, we encounter something even more profound waiting in the darkness beyond our solar system's edge. The space that surrounds us pulses with echoes from the universe's infancy, carrying whispers of events so ancient they predate the formation of our sun by billions of years. Imagine for a moment that you could somehow step outside of time itself and watch the universe unfold like a cosmic flower blooming in slow motion. You would see our solar system as just one tiny eddy in vast currents of matter and energy that have been flowing through space since the earliest epochs of cosmic history. Above and below our familiar planetary realm, these currents continue to shape the architecture of reality in ways both subtle and profound. The intergalactic medium that fills the space between galaxy groups represents one of the universe's most pristine reservoirs of primordial material. This tenuous plasma, heated to millions of degrees by gravitational compression and shock waves, retains the chemical signature of the Big Bang itself. Hydrogen and helium in their original proportions, largely uncontaminated by the nuclear alchemy of stellar cores, drift through these vast spaces like cosmic memories of creation's first moments. Above our solar system, extending toward regions where galaxy clusters mark the intersections of cosmic filaments, this intergalactic medium becomes a laboratory for studying physics under conditions impossible to replicate on Earth. Magnetic fields stretched across millions of light years accelerate particles to energies that dwarf our most powerful accelerators, creating natural experiments that probe the fundamental nature of matter and energy. The cosmic web that surrounds our local galactic neighborhood operates like a vast circulatory system, channeling matter and energy between different regions of the universe across billions of years. Dark matter filaments serve as invisible highways along which galaxies migrate through space, following gravitational currents that operate on scales so large they challenge our ability to visualize them. Within this cosmic circulatory system, our local group represents just one node in a network that extends across the observable universe. The gravitational flows that carry us through space connect us to structures so distant that their light left them when the universe was young and the first galaxies were just beginning to form from primordial gas clouds. Below our solar system, in directions that point toward the cosmic voids that separate these great filaments of matter, we encounter regions where the fabric of space-time itself takes on different characteristics. Here, in the vast emptiness between galaxy clusters, dark energy dominates the local energy budget so completely that space expands at rates approaching the theoretical maximum allowed by cosmic inflation. These voids are not merely empty spaces, but active participants in the universe's evolution. Their expansion creates pressure waves in the surrounding cosmic web, influencing the formation and evolution of galaxy clusters along their boundaries. The interface between void and filament becomes a dynamic frontier where cosmic structure continues to evolve even in the present epoch. The quantum vacuum that pervades these cosmic voids hums with activity at scales so small they exist at the boundary between physics and philosophy. Virtual particles materialize from the void itself, borrowing energy from the universe's quantum foundation, before vanishing again in time frames so brief they challenge our concepts of existence and non-existence. This quantum foam, as physicists call it, may hold the key to understanding dark energy's mysterious nature. The energy density of the quantum vacuum, while incredibly small on human scales, becomes significant when multiplied across the vast volumes of cosmic voids. Some theoretical models suggest that the accumulation of quantum vacuum energy across these enormous spaces could account for the observed acceleration of cosmic expansion. Above and below our solar system, gravitational waves from the universe's most violent events continue to propagate through space-time like ripples on a cosmic pond. The mergers of supermassive black holes in distant galaxy centers create disturbances so powerful they can be detected billions of years after the original events, carrying with them information about conditions in the early universe when such mergers were more frequent. These ancient gravitational wave signals overlap and interfere with each other, creating a complex background of space-time distortions that tells the story of cosmic evolution through the language of geometry itself. Future gravitational wave detectors may be sensitive enough to decode this background signal, revealing details about the universe's history that cannot be accessed through electromagnetic observations. The cosmic neutrino background that permeates all of space represents another fossil relic from the universe's youth. These primordial neutrinos, produced in the first moments after the Big Bang, continue to stream through space at nearly the speed of light, carrying with them information about conditions when the universe was less than a second old. Unlike the cosmic microwave background, which comes from a time when the universe was already 380,000 years old, the cosmic neutrino background provides a direct window into the universe's earliest moments. These ancient particles last interacted with matter when the universe was so hot and dense that the fundamental forces of nature operated under conditions we can barely comprehend. The space above our solar system resonates with these primordial neutrinos, invisible messengers from creation's first instance that continue their journey across cosmic time. Detecting these ancient particles remains one of the greatest challenges in experimental physics, but success would provide unprecedented insights into the conditions that shaped the universe's initial evolution. The magnetic fields that thread through intergalactic space create invisible sculptures in the cosmic medium, guiding the flow of charged particles across distances that span significant fractions of the observable universe. These fields, generated by the rotation of galaxies and the accretion of matter onto supermassive black holes, extend far beyond their sources to create a magnetic web that connects distant regions of space. Where these magnetic field lines converge and reconnect, they release enormous amounts of energy in processes that can accelerate particles to the highest energies observed in cosmic ray detectors. These magnetic reconnection events, occurring in the space above and below our solar system, represent some of the most efficient particle acceleration mechanisms known to physics. The cosmic ray particles accelerated in these distant magnetic reconnection events eventually reach our solar system after journeys that may last millions of years. Along the way, they interact with magnetic fields, interstellar gas, and radiation fields, creating secondary particles and electromagnetic cascades that carry information about the environments they have traversed. Some of the most energetic cosmic rays that strike Earth's atmosphere may have originated in active galactic nuclei so distant that their light has been traveling toward us since the universe was a fraction of its current age. These ultra-high energy particles carry with them encoded information about conditions in the early universe, when quasars were more abundant and supermassive black holes were growing rapidly through accretion. The gamma-ray bursts that occasionally illuminate the space above and below our solar system represent some of the most energetic events in the observable universe. These brief flashes of high-energy radiation, lasting from milliseconds to minutes, release more energy than our sun will produce in its entire lifetime, creating beacons visible across cosmic distances. Long-duration gamma-ray bursts mark the death throes of massive stars in distant galaxies, while short-duration bursts signal the collision of neutron stars or neutron-star black hole pairs. The afterglows from these events fade over days to months, creating temporary new stars in our sky that carry information about stellar evolution and nuclear physics under the most extreme conditions imaginable. The space around our solar system occasionally lights up with these distant fireworks, reminders of the violent processes occurring throughout the universe. Each detected gamma-ray burst provides a snapshot of conditions in its host galaxy at the time of the explosion, allowing astronomers to study star formation, metallicity, and galactic evolution across cosmic time. The expansion history of the universe itself is written in the space above and below our solar system through the redshift of distant galaxies and the cosmic distance ladder built from standard candles like Type 1a supernovae. This expansion, initially driven by cosmic inflation and later by dark energy, has stretched the wavelengths of ancient photons and created the cosmic redshift that serves as our primary tool for measuring cosmic distances. The accelerating expansion discovered through observations of distant supernovae revealed that the universe's expansion is not slowing down under the influence of gravity, as had been expected, but is instead speeding up due to the mysterious influence of dark energy. This acceleration affects the space around our solar system in subtle but measurable ways, influencing the rate at which distant galaxies recede from us. The cosmic horizon that limits our observable universe is constantly evolving as space continues to expand. Galaxies that are currently visible to our telescopes will eventually recede beyond this horizon, disappearing from view as space itself carries them away at velocities exceeding the speed of light. The space above and below our solar system will gradually empty as the cosmic expansion carries distant structures beyond the reach of even our most powerful future observatories. This cosmic loneliness represents the ultimate fate of our local galactic neighborhood if dark energy continues to dominate the universe's expansion. In the far future, observers in our galaxy will see an apparently empty universe, with only the closest gravitationally bound structures remaining visible against the cosmic microwave background. The quantum fields that permeate every cubic centimeter of space above and below our solar system participate in this cosmic expansion through mechanisms we are only beginning to understand. The Higgs field, which gives mass to fundamental particles, extends throughout the universe and may play a role in determining the rate of cosmic expansion through its interactions with dark energy. Other quantum fields, including those associated with particles we have not yet discovered, may contribute to the universe's energy density in ways that affect its expansion rate. The space around our solar system may be filled with exotic forms of matter and energy that interact only gravitationally, contributing to the dark sector that dominates the universe's mass-energy budget. The search for dark matter particles continues in laboratories deep underground, where sensitive detectors wait for the rare collision between a dark matter particle and an atomic nucleus. The space above and below our solar system streams with these invisible particles, creating a dark matter wind as our solar system moves through the galactic halo. Seasonal variations in dark matter detection rates could reveal the orbital motion of Earth through this dark matter wind, providing direct evidence for the existence of these elusive particles. The failure to detect dark matter particles, despite decades of searching, has led to increasingly exotic theoretical proposals, including the possibility that dark matter consists of primordial black holes or other objects that interact only gravitationally. The axion field, if it exists, would permeate all of space above and below our solar system, oscillating at frequencies determined by the axion mass. These oscillations would create subtle effects in electromagnetic fields that might be detectable with sufficiently sensitive instruments, potentially revealing the presence of this hypothetical particle that could account for dark matter. Laboratory searches for axions use powerful magnetic fields and sensitive microwave detectors to look for the conversion of axions into photons, a process that would occur continuously as the axion field oscillates. The space around our solar system would be filled with these axions, creating a background signal that could potentially be detected if the technology becomes sensitive enough. The sterile neutrinos that may populate the space above and below our solar system represent another candidate for dark matter, particles that interact even more weakly with ordinary matter than conventional neutrinos. These hypothetical particles would be produced in the early universe and would continue to stream through space, contributing to the overall dark matter density. Detecting sterile neutrinos would require observing their subtle effects on the oscillations of conventional neutrinos or their gravitational influence on cosmic structure formation. The space around our solar system may contain vast numbers of these particles, invisible to direct detection, but potentially observable through their collective gravitational effects. As we contemplate these invisible components of the cosmos, we begin to realize that the familiar matter that makes up stars, planets, and living beings represents only the visible tip of a much larger iceberg. The space above and below our solar system teems with exotic particles, fields, and energies that we are only beginning to discover and understand. This hidden universe operates according to physical principles that extend far beyond our everyday experience, governed by quantum mechanics at the smallest scales and general relativity at the largest. The intersection of these two great theories in the quantum gravity regime may hold the key to understanding the deepest mysteries of cosmic structure and evolution. The holographic principle suggests that all the information contained in a volume of space can be encoded on its boundary, implying that the three-dimensional space above and below our solar system may be a projection of information stored on a distant two-dimensional surface. This radical idea challenges our basic assumptions about the nature of space and time, suggesting that reality may be far stranger than we imagine. String theory proposes that the fundamental constituents of matter and energy are not point particles but tiny vibrating strings existing in dimensions beyond the three spatial dimensions we observe. The space around our solar system may be embedded in a higher dimensional structure where these extra dimensions are curled up so tightly that we cannot detect them directly. The landscape of possible string theory solutions includes an enormous number of different vacuum states, each corresponding to a different set of physical laws and constants. Our observable universe may represent just one of countless bubbles in a vast multiverse, where every possible combination of physical parameters is realized somewhere. The eternal inflation that may have preceded the Big Bang could continue to operate in regions beyond our cosmic horizon, constantly creating new bubble universes with different physical properties. The space above and below our solar system may be connected to this larger multiverse through quantum tunneling events that are too rare to observe directly, but may leave subtle signatures in the cosmic microwave background. Loop quantum gravity offers an alternative to string theory, proposing that space and time themselves are quantized at the smallest scales. In this view, the apparently smooth space-time above and below our solar system is actually composed of discrete units of space and time, creating a granular structure that becomes apparent only at the Planck scale. The implications of quantum gravity extend far beyond theoretical physics, potentially affecting our understanding of black holes, the Big Bang, and the fundamental nature of reality itself. The space around our solar system may exhibit quantum gravitational effects that are currently too subtle to detect, but could become observable through these contemplations of the deepest mysteries of existence. We find ourselves at the intersection of physics and philosophy, where scientific with future advances in experimental technique. As we float, observation meets the limits of human comprehension. The space above and below our solar system serves as a vast laboratory where the universe conducts experiments in fundamental physics that we are only beginning to decode. Every photon that reaches our telescopes, every gravitational wave that passes through our detectors, every cosmic ray that strikes our atmosphere carries encoded within it information about processes operating under conditions of extreme energy, density, and curvature principles of reality. By observing their effects in the space that surrounds us, the journey cannot be replicated on Earth. We are students of the cosmos. Learning about the deep through these cosmic realms reveals that our solar system exists not in isolation, but as an integral part of a universe that is far more interconnected, dynamic, and mysterious than previous generations could have imagined. We are embedded in cosmic flows that operate across scales from the quantum to the cosmological, temporary arrangements of matter and energy that have somehow achieved the ability to contemplate their own cosmic context. In understanding what lies above and below our familiar planetary neighborhood, we gain perspective on our place in the grand narrative of cosmic evolution. This understanding transforms our view of human existence from that of isolated observers to active participants in the universe's ongoing quest to understand itself through the emergence of consciousness and curiosity in creatures like ourselves. The space that surrounds our solar system is not empty void, but a rich tapestry of physical processes, invisible particles, and cosmic connections that link us to the most fundamental questions about the nature of existence. As we continue to develop the tools and techniques needed to explore these cosmic mysteries, we inch closer to answers that may revolutionize our understanding of reality itself. Tonight, as you drift towards sleep, remember that you are floating through space on a small world that participates in cosmic processes of unimaginable scale and complexity. The atoms in your body were forged in stellar cores. The space around you hums with invisible particles and fields, and the very fabric of space-time carries information from the most distant reaches of the observable universe. Above and below our solar system lies not just empty space, but a cosmos alive with mystery, beauty, and connections that bind us to the deeper secrets of existence. In contemplating these vast realms, we touch something profound about what it means to be conscious beings in a universe that appears designed to eventually understand itself through eyes like ours, minds like ours, hearts capable of wonder. The cosmic web that cradles our solar system operates like an infinite neural network, with dark matter filaments serving as synapses that carry information across billions of light years. These invisible pathways pulse with gravitational signals, connecting galaxy clusters in a vast pattern of communication that has been evolving since the universe's earliest epochs. Within this cosmic neural network, our local group functions as just one small cluster of neurons, processing gravitational information from across the observable universe. The signals that flow through these dark matter highways carry with them the accumulated wisdom of billions of years of cosmic evolution, encoded in the subtle variations of gravitational potential that guide the motion of galaxies through space and time. The space above our solar system participates in this cosmic information, processing through mechanisms that operate at the intersection of quantum mechanics and general relativity. Virtual particles that materialize from the quantum vacuum carry momentum and energy across microscopic distances, while gravitational waves propagate these effects across cosmic scales, creating a hierarchy of information transfer that connects the smallest and largest structures in the universe. Every cubic centimeter of space around our solar system contains roughly 400 cosmic microwave background photons, ancient messengers from the universe's youth that continue their journey through space, carrying encoded information about conditions when the cosmos was only 380,000 years old. These photons interact constantly with the quantum fields that permeate empty space, exchanging energy and momentum in processes so subtle they exist at the boundary between the measurable and the theoretical. The electromagnetic zero-point field that fills the space above and below our solar system creates fluctuations in the vacuum that may be responsible for some of the most fundamental properties of matter. These quantum fluctuations, while individually tiny, accumulate across the vast volumes of intergalactic space to create effects that may influence the large-scale structure of the universe itself. Dark photons, if they exist, would populate the space around our solar system as invisible cousins to ordinary light, carrying information through hidden electromagnetic fields that interact only weakly with the matter we can observe directly. These hypothetical particles could serve as messengers between our visible universe and dark sectors of reality that remain completely hidden from conventional observation. The cosmic neutrino background that permeates all of space represents the most abundant form of matter in the universe after photons, with roughly 330 relic neutrinos from the Big Bang present in every cubic centimeter. These primordial particles, cooled by billions of years of cosmic expansion, carry with them information about the universe when it was less than 1 second old, and the fundamental forces operated under conditions of unimaginable energy density. Above our solar system, in directions that point toward the cosmic microwave background's cold spot, we encounter regions where the ancient radiation appears slightly cooler than average. This temperature anomaly, spanning billions of light years across the sky, may represent evidence of our universe's collision with another bubble universe in the primordial epoch, a cosmic scar that preserves information about physics operating beyond our current understanding. The supervoids that exist in these directions create gravitational wells so vast they affect the energy of photons traveling through them. Light from the cosmic microwave background loses energy as it climbs out of these enormous gravitational potential wells, creating temperature decreases that serve as fossil evidence of the universe's largest structures. Below our solar system, extending toward regions where the cosmic web creates dense knots of dark matter, we find concentrations of invisible mass so significant they bend space-time in ways that affect the propagation of light across cosmic distances. These gravitational lenses magnify and distort the images of distant galaxies, creating cosmic telescopes that allow us to observe objects that would otherwise be too faint to detect. The Einstein rings and gravitational arcs created by these massive structures encode information about the distribution of dark matter along the line of sight, revealing details about invisible cosmic architecture through the geometry of bent light. Each gravitationally lensed galaxy serves as a probe of the dark matter distribution, allowing astronomers to map the invisible scaffolding that supports visible cosmic structure. Strong gravitational lensing events can magnify distant galaxies by factors of hundreds or thousands, creating natural telescopes that allow us to observe star formation in galaxies so distant their light has been traveling toward us for most of cosmic history. These cosmic magnifying glasses reveal details about the early universe that would be impossible to observe through any other technique. The time delays between multiple images of the same gravitationally lensed object provide direct measurements of cosmic distances and expansion rates, creating independent tests of our understanding of dark energy and cosmic acceleration. The space above and below our solar system serves as a laboratory for these precision cosmological measurements, each lensing event contributing to our understanding of the universe's expansion history. Gravitational microlensing events, caused by individual stars or planets passing in front of distant background sources, create brief brightening events that can reveal the presence of otherwise invisible objects throughout our galaxy. The space around our solar system occasionally experiences these cosmic alignments, where distant stars serve as natural laboratories for studying the distribution of dark matter and rogue planets. The cosmic shear created by the gravitational influence of large-scale structure causes systematic distortions in the shapes of distant galaxies, creating a weak lensing signal that maps the distribution of dark matter across the observable universe. This cosmic cartography reveals the invisible architecture that guides the formation and evolution of cosmic structure on the largest scales. Above our solar system, the Baryon acoustic oscillations frozen into the cosmic microwave background create a standard ruler that allows astronomers to measure cosmic distances with extraordinary precision. These acoustic waves, generated by sound waves propagating through the primordial plasma, left their imprint on both the cosmic microwave background and the large-scale distribution of galaxies. The characteristic scale of these Baryon acoustic oscillations, roughly 500 million light-years in the current universe, provides a cosmic yardstick that can be used to trace the expansion history of space itself. By measuring how this standard ruler appears at different redshifts, astronomers can chart the influence of dark energy across cosmic time. The space below our solar system contains galaxy surveys that reveal this acoustic signature in the clustering patterns of millions of galaxies, creating three-dimensional maps of cosmic structure that extend billions of light years in all directions. These surveys transform distant galaxies into tracers of the underlying dark matter distribution, revealing the cosmic web in unprecedented detail. Redshift space distortions in these galaxy surveys provide additional information about the growth rate of cosmic structure, testing our understanding of gravity on cosmic scales. The peculiar velocities of galaxies, induced by gravitational interactions with surrounding dark matter, create systematic patterns in redshift surveys that encode information about the strength of gravitational clustering. The integrated Sachs-Wolf effect creates temperature fluctuations in the cosmic microwave background as photons travel through evolving gravitational potential wells, providing another probe of dark energy's influence on cosmic structure formation. The space above and below our solar system participates in this effect as cosmic expansion changes the depth of gravitational wells along photon paths. Cross-correlations between the cosmic microwave background and galaxy surveys reveal the signature of this integrated Sachs-Wolf effect, providing independent evidence for the accelerating expansion of space. These correlations connect the most ancient light in the universe with the current distribution of matter, creating bridges across cosmic time that test our understanding of cosmic evolution. The kinetic Sunyaev-Zeldovich effect, caused by the motion of galaxy clusters through the cosmic microwave background, creates temperature fluctuations that can be used to measure the velocities of massive structures across cosmic distances. The space around our solar system occasionally lies along the line of sight to these moving clusters, allowing us to observe their motion through space. This effect provides direct measurements of the cosmic flow patterns driven by gravitational attraction toward massive structures like the Great Attractor and the Shapley supercluster. The space above and below our solar system participates in these large-scale motions, carried along by gravitational currents that operate on scales much larger than our local galactic neighborhood. The thermal Sunyaev-Zeldovich effect reveals the hot gas that pervades galaxy clusters, creating temperature decrements in the cosmic microwave background that maps the distribution of baryonic matter on cluster scales. This effect allows astronomers to detect galaxy clusters regardless of their distance, creating surveys that trace cosmic structure formation across most of the universe's history. The space surrounding our solar system occasionally lies within the projected boundaries of these distant clusters, allowing us to observe how hot intracluster gas affects the propagation of cosmic microwave background photons. These observations provide insights into the physics of structure formation and the thermodynamic history of baryonic matter. Cosmic voids, the vast empty regions between galaxy filaments, create their own signatures in the cosmic microwave background through the integrated Sachs-Wolf effect. Photons traveling through these underdense regions gain energy as they fall into the voids and lose less energy climbing out, creating net temperature increases that map the universe's largest empty spaces. The space above and below our solar system contains lines of sight that pass through some of the universe's largest voids, regions so empty they contain less than 10% of the average cosmic density of matter. These cosmic deserts, hundreds of millions of light years across, represent the flip side of cosmic structure formation, showing us what happens in regions where gravity failed to collect matter into dense concentrations. The local void, located roughly in the direction of the constellation Bertas, represents one of the nearest large voids to our position in the cosmic web. This region of extremely low galaxy density may influence our local gravitational environment, contributing to the peculiar motion of our local group through space. Void galaxies, the rare objects that exist in these cosmic deserts, provide unique laboratories for studying galaxy formation in underdense environments. These isolated systems evolve differently from galaxies in dense clusters, often showing enhanced star formation rates and unusual morphologies that reflect their lonely cosmic circumstances. And so we reach the end of our cosmic journey, having traveled from the familiar realm of planets to the very edges of existence itself. We've witnessed how our solar system floats within an ocean of invisible dark matter streams, bathes in ancient light from the universe's infancy, and participates in gravitational dances that span billions of light years. Above and below our small corner of space lies not emptiness, but a vast tapestry of quantum fields, cosmic web filaments, and primordial echoes that connect us to the deepest mysteries of reality. As you drift into sleep tonight, remember that you are part of this magnificent cosmic story, made of atoms forged in dying stars, surrounded by invisible forces that have shaped the universe since time began. Sweet dreams, fellow traveler in this endless cosmic dance.